Let's understand the capacitor. A capacitor is a device which is used to store energy in the form of electric field lines. Let me explain. Suppose we have an arrangement and we give some charge to it, and due to this charge there will exist field lines around it, and we know that these field lines carry energy density. So any small element of the space, suppose this is if we consider a small volume near it, the field lines will have energy density. So this volume will have some energy given as energy density into its volume. As surrounding has some energy stored, so this can behave as a capacitor. This can behave as a capacitor. Take another situation. If we have a conductor, like this one is A and this is B, and we have supplied charge plus Q to this one and minus Q to this one, there will exist field lines between them from positive charge to negative charge, like this, and in the region between them electrostatic energy will be stored. So this system behaves as a capacitor. How will we define the capacitance? Capacitance is the property of a system to store energy in the form of charge. It can be a metal or a conductor. Metal or a conductor. So if we define the capacitance of this system, we see that if we increase the charge, the potential difference between them will increase. Charge is proportional to potential difference. So we can write as Q is equal to, if we remove this proportionality, some constant into potential difference, and this constant is known as capacitance. Capacitance is equal to charge per unit potential difference. For this system, we will write as capacitance AB as Q divided by VA minus VB. The SI unit of capacitance is farad. SI unit of the capacitance, SI unit is farad. 1 farad is typically very large, so we use a smaller unit like microfarad, 10 to the power minus 6 farad, or nanofarad, 10 to the power minus 9 farad, or even a smaller like picofarad, 10 to the power minus 12 farad. Now, for example, if we have a sphere, conducting a sphere, and we want to find the capacitance of that sphere. Example, we have this sphere and we want to find the capacitance of this system. If we will supply the charge, we assume that we have supplied some charge to it, and there will be electric field lines nearby originating from it going to infinity. Its potential will be V is equal to, if this charge is Q, V will KQ by R, or 1 by 4 pi epsilon naught R, Q by R. So the capacitance of the sphere is equal to the charge divided by potential difference. Potential difference means potential of the sphere minus potential up to which the field lines are going. Q, V, potential at the surface minus potential at infinity, and we know that potential at infinity is 0. So this will be Q upon this potential 1 by 4 pi epsilon naught Q by R. Q gets cancelled, and this is 4 pi epsilon naught R. This comes out to be capacitance. One interesting thing to note that this capacitance do not depend on the charge, neither it depends on the potential of the sphere. This is the constant for this system, and it should be. The common sense says that the capacity should not depend on the contents or the material which it possesses. For example, if we have a bottle, water bottle, if either it is filled partially or wholly or halfway, but its capacity will be always be fixed. The amount of matter it can contain, it will always be fixed. About the factors affecting the capacitance, the factors on which capacitance of the system depend. First is shape, size and geometry of the system. This one is shape, size and geometry of system. And second one is a stability of surrounding medium. Stability of surrounding medium. Let me explain. If we have a conductor like this, any arbitrary shaped conductor, and we supply the charge to it, as we will keep supplying the charge, its potential will increase. Potential will increase, the field will increase, charge density will appear in its surface. But since the surface is irregular, it will be non-uniform charge distribution. So at the sharp point like this, the charge density will be higher. And we know that electric field nearby a conductor is given by E is equal to sigma by epsilon naught, where sigma is the charge density, epsilon naught is the permittivity, or epsilon is permittivity of the medium surrounding it. So as we keep on increasing the charge, the field around it will increase. So the field near the sharp point will be excessively high, and a point will be reached where this will start leaking. The charge will start leaking from this sharp point. That means this limits the capacitance of the system. The shape of the conductor greatly determines the capacitance of the system. For example, if we have like this capacitor, at this point, the local charge density, we know that the conductor is equipotential surface. So for equipotential surface, sigma r is constant, or the local charge density is inversely proportional to radius of curvature near this. This radius of curvature is smaller and this one is bigger. So the charge density here will be more. So the electric field will be more. And here the charge density will be small and the electric field will be small. E1 is greater than E2. At some point, if we keep supplying the charge, at some point this electric field can reach the breakdown voltage of this medium and the charge will start leaking out. So it will limit the capacity to have the charge on the surface. So the shape, size and geometry determine the capacitance of the system. And the another one is a stability of the surrounding medium. If we see that the surrounding medium, for example, if it is air, the molecules of the air are neutral, like this one. The molecules of the air are neutral. But if we apply electric field, it will shift, the charges center will shift like this. The positive charge will be repelled and negative charge will be attracted. If we keep on increasing this charge, the electric field at this point will keep on increasing, and a time can come that this molecule can break apart, and this is called as the dielectric breakdown. For air, this dielectric breakdown is 3 into 10 to the power 6 volt per meter. This is the maximum electric field which can it withstand. So these two factors affect the system, the capacitance of the system greatly. So please, now we see the energy stored in a capacitor. Suppose we have a capacitor and we are charging it, we are supplying the charge. Initially when there was no charge, at t is equal to 0, there was no potential. So the incoming charges will not feel any kind of a repulsion. So no work done initially. But as it will acquire some charge, we will have to do some work. We will have to do some work against these charges. So we can say that if it has a charge Q and its capacitance is C, and we are bringing very small amount of charge dq, we have to do work, very small little work, dw is equal to the potential V into a small charge, and this work done will keep on adding as we are adding the charge. This work done will be increased, and the total work done will be equal to this energy stored of the capacitor. So if we say that energy stored is equal to this total work done to accumulate the charge, or V dq, this will be the energy stored by this capacitor. We can write this V as Q by C dq, and this will come as 1 by C outside, Q dq. This will be equal to charges from 0 to Q. 0 to Q, this will be equal to potential energy stored by this capacitor is equal to Q square by 2C. We can write this in another form too. If we can write, this is the total charge stored by this capacitor and V is the potential, and we have Q is equal to CV, and if we put this Q is equal to CV in this equation, we will have Q is equal to CV square divided by 2C, that is half of CV square. Yes. Next we see the types of capacitor. First we have the parallel plate capacitor. What is a parallel plate? If there is a large metal plates are separated by very small distance, then we can say that this arrangement is a parallel plate capacitor. For example, if there are two plates like this, and they are separated by very small distance d, and we supply some charges, and it is such that its area A is very small, smaller than d, or we can say that this d is very smaller than the linear size of this plate. Linear size means this square root of A. Then this system can be said as parallel plate capacitor. How the capacitance will depend on this, let us see. So if we supply charges on the plate, suppose we have supplied plus Q on this one and minus Q on this one, inner faces, the charge density will appear like this. We have supplied Q charge on the inner surface and minus Q charge on this plate. So now we can write this charge density is Q by A, charge per unit area, and electric field lines will exist due to this plate as well as due to this plate E2, and since they both are identical, charge densities are same, this E1 will be equal to E2. E1 will be equal to E2, and we know that for an infinite large plate, the electric field lines nearby it is given by sigma by 2 epsilon naught. This will be the electric field lines, electric field. So the net electric field at any point P can be given as E1 plus E2 due to positive plate the electric field in this direction, and negative plate also the electric field in the same direction. So they will add up, and this will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught equal to sigma by epsilon naught. And now this electric field is constant because this region is very small. So if you write the potential difference between the plate, potential difference between plate, we can write as V is equal to E into D, V or delta V, and this will be sigma D by epsilon naught. And for this system, if we have to define the capacitance will be C is equal to charge divided by potential difference. Charge can be written as sigma into A divided by sigma D by epsilon naught. Sigma gets cancelled, and this comes out to be sigma epsilon naught A divided by D. This is the capacitance of this system, where epsilon naught is permittivity of medium and permittivity of vacuum. If there is a medium between them, we will take the permittivity of that medium. A is the area of the plates, and D is the separation between the plates. Let us take an example. Suppose we have a plate of area 1 meter square. 1 meter square is quite large, but just we are trying to calculate the capacitance of a system. We have the plate area 1 meter square, and the separation between them is 1 millimeter. 1 millimeter. If we find the capacitance, it will be epsilon naught A by D. Epsilon naught for the air capacitor, 8.85 into 10 to the power minus 12 into area 1 divided by 1 millimeter is 10 to the power minus 3 meter. This comes out to be 8.85 into 10 to the power minus 9, or 8.85 nanofarad. That means this is for, even for this large arrangement, 1 meter square area, this capacitance is very, very small. So how do we increase the capacitance of the system? To increase this capacitance, we place a medium inside it, that is known as dielectric. So let us see what is the effect of dielectric in a capacitor. Suppose we have a capacitor, and its capacitance is C naught given by epsilon naught A divided by D. And now we have inserted a medium dielectric. What is a dielectric? First understand. Dielectric is anything which is not a conductor. That means this medium has not enough free electron. So when we will insert inside the capacitor, the net electric field inside this medium will not be zero. It will have some electric field. This is the dielectric of some dielectric constant. So this was the electric field E naught, and inside this electric field is reduced. Like if it is dielectric constant of K, then the electric field will be E naught by K. So electric field has reduced. If electric field will reduce, that means this potential difference will be reduced, and the potential difference will be reduced. Then the capacitance of the system C dash is equal to Q by delta V. This has reduced, so the capacitance will increase. It will increase. How it will increase? If it was initially, this potential difference was V naught. Now this potential difference will be V naught by K, because electric field has decreased by the factor of K, so the potential difference will also decreasing by the factor of K. So V naught by K. So the new capacitance will be given as Q upon V naught by K, or K times of Q upon V naught, and Q upon V naught was initial capacitance. So this is K upon C naught. So C dash, the new capacitance, is equal to K times of initial capacitance without the dielectric. Or we can say that K times of epsilon naught E by D.